So we have a rock. I think we should first draw a free body diagram. Force tension is so the rock is being connected to a rope. And then we have a buoyant force. Some water. Then we have a buoyant force that is pushing the rock upward. And then we have, of course, the weight of the rock due to gravity. The weight of the rock due to gravity is simply going to be mg. And this is going to be 1.8 times 9.8. This is simply going to be 17.64 newtons. So this is the weight of the rock. Now we need to find the buoyant force first. This will be sigma F in the y direction is equaling Fg minus Ft minus the buoyant force. So the force of gravity minus the force of tension minus the buoyant force. This is going to be equal 0 because we don't want the rock to be moving up or down. So this is going to equal 0. And we find that the buoyant force is simply equal to the force of gravity minus the force tension. Plugging in for our constants, we have 17.64. And then the problem tells us that the force tension is 12.8 newtons. We find that the buoyant force is equaling 4.84 newtons. At this point, we can find the volume needed. So here we can say that the buoyant force is equal to the density of the water times the acceleration due to gravity times the volume of the water. Here, we're going to have to solve and isolate V. So V is going to equal the buoyant force divided by the density of the water times gravity. Plugging this in, we find that we plug in our constants first. So 4.84 divided by 1,000 kilograms per cubic meter, and then times 9.8 meters per second squared. This is going to equal 4.94 times 10 to the negative fourth meters cubed. At this point, we find the volume of whatever whatever liquid this rock is being submerged in. So if we have this particular volume and the rock needs to float, this means that we can say that in order for the rock to float, the buoyant force must equal the force of gravity. Here we have, again, the buoyant force is equal to the density times gravity times the volume, and this is going to equal mg. Gravity is on both sides, and then, of course, we're trying to solve for the density. The density of whatever liquid, the density of a certain liquid, such that this liquid will allow the rock to float on it. Here, we're going to isolate density, so rho equals m over v. And for the mass, we're going to be using the mass of the rock, so 1.8 kilograms. And then for the volume, we'll be using the volume that we found in the previous slide of 4.94 times 10 to the negative fourth meters cubed. At this point, we find that the density is equaling 3,643.72 kilograms per meter cubed. So this is the density of a liquid such that the rock will float upon it. So this is the minimum density, given that the rock floats. And that's the end of the solution. Thank you for watching.